Good evening, Raja. Good evening, Netra. Good evening, Tanishka.
Good evening, ma'am.
Good evening, ma'am.
Raja, are you there? All right. So we're going to start a new chapter, volumes and surface areas. Let's see the introduction to this chapter. So the first solid you see here is a cube. Now we say that the cross section of a cube is a square. The cross section of a cube is a square. Now what do we mean by that? Now supposing you have many identical squares, okay? You have many identical squares. Identical squares meaning squares of the same size. Supposing 4 centimeters by 4 centimeters, you have many squares like this. Say made of paper, 4 centimeter by 4 centimeter. Now when you stack, when you arrange these squares, when you arrange these squares to a height of 4 centimeters. So see, this is that square paper of side 4 centimeter. So you stack the identical squares to a height of 4 centimeters, to a height of 4 centimeters. So then you get a solid. The square is a plane figure. Square is a plane figure because it has only length and breadth. It does not have thickness. Now, when a plane figure assumes a thickness, how can that happen? So when you stack identical squares, now here the squares are of length 4 centimeters. So you stack it to a height of 4 centimeters. Then the solid obtained is a cube of edge 4 centimeters because the length is 4, the breadth is 4, and the height also is 4 because you have stacked up the papers to a height of 4 centimeters. So we say that the cross section of a cube is a square. The cross section of a cube is a square. See, I'll repeat. So supposing you have many identical squares, okay, cut out of paper of side, say 5 centimeter. You have many identical squares like this of side 5 centimeters. Now, what you do is you stack the squares. Squares are plane figures. You stack it, you place it one over the other, like you arrange your books in the shelf, no? You place the books one over the other, you stack them up. So like that, you stack the squares. You place the squares one over the other. So to what height? To a height of 5 centimeters. You keep stacking the squares to a height of 5 centimeters because the length and the breadth of the square is 5. So you'll have to go on to get a height of 5 centimeters. Then the solid obtained is a cube of edge 5 centimeters. So since a cube is a solid obtained by stacking identical squares to a particular height, whatever is the length and the breadth of the square, to that height you'll have to stack the squares. So we say that the cross section of a cube is a square. The cross section of a cube is a square. Now, how do we understand volume? Volume is the area of the cross section into height of the solid. Volume is area of the cross section into height of the solid. So when we talk about a cube, the area of the cross section or the cross section is a square. And what is the area of the square? A square. Into height of the cube. We stack it to the same height, right? Whatever is the length and the breadth of the square, that will be the height of the cube. So A, what is the length and the breadth of the square? A. So height is A. So A square into A cubed cubic units. A cubed cubic units. So volume is given by area into height. Volume is equal to area into height. Area into height. Area is area of the cross section, which is a square. The area of the square is A square. Into the height, the cube has assumed is A. So A cubed cubic units is the formula to find the volume of a cube. Curved surface area. Now we know that a cube has 6 faces. A cube has 6 faces. See here, this is the bottom face, 1. This is the top face, 2. This is the front face, 3. This is the back face. Behind there's a face, no, 4. The side face, 5, and this side face, 6. So a cube has 6 faces. A cube has 6 faces. It has one face on the top, one square face on the top, one square face at the bottom, and 2 square faces on the sides, the left side and the right side. And there is one face, square face in the front and one square face behind. So this is the back face here. This is the back face. This is the front face. The side faces, these are the side faces. And this is the top face. This is the bottom face. So when we say curved surface area, and of these 6 faces, 4 faces are vertical. The side faces are vertical. See these faces, the side faces, they're standing, no, this one, 2, this one and the front face. The 2 faces in the front and back, they're standing up, they are vertical faces. And the 2 faces on the sides, the left side and the right side, they are also standing. So they are called the 4 vertical faces. The top and the bottom face, they are horizontal. The top and the bottom face are horizontal. They're like sleeping. The top face and the bottom face are horizontal. The side faces, they're vertical, they're standing. The side faces and the front and back face, they're standing. These 4 vertical faces are called these 4 vertical faces make the curved surface area of the cube. So curved surface area meaning the area of the 4 faces, the 4 vertical faces. Curved surface area is the area of the 4 vertical faces. This face which is standing, the left face, the back face, the right side face, and the front face, they're all standing. These 4 faces make the curved surface area. So curved surface area is expressed as perimeter of the cross section into height. CSA is expressed as perimeter of the cross section into height. Now the cross section is a square and the perimeter of the square is 4a, and the height of the cube is a. So 4a square, 4a square units. We can also derive the curved surface area like this. The area of the front face is a square. The area of the back face is a square because all are squares. The area of the side face is a square. And the area of the 2 side faces, a square plus a square. So 4a square units. You can also do it like this. Curved surface area is the area of the 4 vertical faces, front, back, left, right. They're all squares. So how will you find the total area? The total area is area of the front face plus the area of the back face plus the area of the 2 side faces. So 4a square. You can say this way, or in general, CSA is equal to perimeter of the cross section into height. The cross section is a square. So perimeter of a square is 4a into height a, 4a square. Next comes the total surface area. Total surface area meaning area of all the 6 faces. Total surface area is the area of all the 6 faces. So that means it is the curved surface area, all the vertical faces, plus the area of the base, plus the area of the top. CSA, the 4 faces, plus the area of the base, plus the area of the top. That is the area of all the 6 faces. Make the total surface area. So what is the curved surface area? 4a square. Area of the base is a square. The base is a square. And the area of the square is a square. The area of the top is also a square. Its area is a square. Its area is a square. So 4a square plus a square plus a square to 6a square units. The total surface area is area of the side face, the curved surface area, that is 4a squared, plus the area of the top, plus the area of the bottom. All right. Now next is the length of the diagonal. The length of the diagonal of a cube. So the diagonal, you can see it here in the figure. The diagonal is the line segment connecting one bottom corner to the opposite top corner. And this will be the longest line segment in the cube. This is the longest line segment in the cube. Like the hypotenuse is the longest side in a right triangle. Correct? The hypotenuse is the longest side in a right triangle. Similarly, in a cube, the diagonal of the cube is the longest line segment in the cube. And it's given by root 3a. So how do we get that? By Pythagoras theorem. By using Pythagoras theorem. See the right triangle here? See the right triangle here? Okay, you can see the right triangle here. Okay, so this is 90 degrees. This is 90. So by using Pythagoras theorem, the square on this side plus the square on this side, you will get the square of the hypotenuse. How do you use Pythagoras theorem? How do you use the theorem? See here, it's like this. This is the diagonal. This is the diagonal. This is the diagonal. This is root 2a, and this is a. So diagonal is equal to root 2a the whole square. Diagonal square is equal to root 2a the whole square plus a square. Pythagoras theorem, that is equal to 2a square plus a square, which is equal to 3a square. So diagonal square is equal to 3a square. So the diagonal will be square root of 3a square, which is equal to root 3a. By using Pythagoras theorem. And how is this root 2a? Because this is square. The bottom is a square. The bottom is a square, and the length of the diagonal of a square is given by the formula root 2a. I've told you this. The length of the diagonal of a square is given by the formula root 2a. The length of the diagonal of a square is given by the formula root 2a. That's how we have a there. So by using Pythagoras theorem, the length of the diagonal is root 3a units. Then finally, the length of all the edges. Now a cube has 12 edges. A cube has 12 edges. Here, let's count the edges. Let's count the edges on the top. 1, 4. 1, 2, 3, 4. Let's count the edges at the bottom. 5, 6, 7, 8. So there are 8 horizontal, edges. On the top we have 1, 2, 3, 4 edges. Bottom we have 5, 6, 7, 8 edges. In all, we have 8 edges like this. Then see the vertical edges 9, 10, 11, 12. So a cube has 12 edges. What is the length of each edge? A units. What is the length of each edge? How much is each of this? A. So what is the length of all the edges? A plus A plus A plus A plus A 12 times. Because there are 12 edges. All the edges have the same length, A units. Because it's a cube. All the edges are equal in length. Everything is A. How many edges does a cube have? 12 edges. What is the length of each edge? A. So all the 12 edges, A plus A plus A plus A 12 times, which is 12A. Got this, children?
Yes, ma'am.
All right. So in the same way, we have a cuboid. So the cross section of a cuboid is a rectangle. So you have, say you have many identical rectangles of length 4 centimeters and breadth 3 centimeters. You have many identical rectangles of length 4 centimeters and breadth 3 centimeters. So now you're free, so you don't know what to do. So what you do, you stack up these rectangles. So you arrange these rectangles. You have many identical rectangles of length 4 units and breadth 3 units. So what you do, you stack these rectangles to any height. See, it's a cuboid. So the height is okay, any height as you please, to any height. When it is a cube, you should be careful. Since the length, breadth, and height are all the same in a cube, you must stack it to a specific height. Supposing the square has a side of 10 centimeters, then you should stack it to a height of 10 centimeters. But this is a cuboid. So you can stack it to any height. When you stack identical rectangles to any height, the solid obtained is a cuboid. The solid obtained is a cuboid. So volume of a cuboid is area of the cross section into height. Area of the cross section into height. So what is it? Area of the cross section. Cross section is a rectangle. Cross section is a rectangle. And what's the area of the cross section, which is a rectangle? L into B. L into B. And what's the height of the cuboid? To any height. You can build it to any height, H. So LBH cubic units is a formula to find the volume of a cuboid. LBH cubic units, area of the cross section into height. Cross section is a rectangle. Its area is L into B into H. Area of the cross section into height is the volume of a cuboid. Next comes the curved surface area. As we understood here, the curved surface area is the perimeter of the cross section into height. Volume is area of the cross section into height. Curved surface area is perimeter of the cross section into height. Same thing here. Curved surface area is perimeter of the cross section into height. And what's the perimeter of a rectangle? 2 into L plus B. Perimeter of a rectangle is 2 into L plus B. Okay, so perimeter of a rectangle. CSA is perimeter of the cross section into height. The cross section is a rectangle, and the perimeter of a rectangle is 2 into L plus B. Perimeter of a rectangle is 2 into L plus B. So that's what you see here. 2 into L plus B, perimeter of the cross section into height, which can be written as 2H into L plus B square units. Total surface area is so curved surface area is the area of the 4 vertical faces. Curved surface area is the area of the 4 vertical faces. Now, a cuboid has 6 faces. Curved surface area has taken 4 faces. Now we have 2 remaining faces, one on the top and one at the bottom. The area of all these faces is the total surface area. So it is a curved surface area, 4 faces, plus the area of the base, plus the area of the top. So the curved surface area is 2H into L plus B. The area of the base, what is the base area? Look at the base. This is the base. This is the base. And its area is L into B. L into B. You can see there. The base is a rectangle. The base is a rectangle. Its area is L into B. And the top is also a rectangle. The top is also a rectangle. The base and the top are both rectangles of length L and breadth B. So area of the base is L into B. Area of the top is also L into B. Then you open up the bracket. You get 2LH plus 2BH plus LB plus LB is 2LB. Open up the brackets, I said. See here, 2LH plus 2BH plus 2LB. Then 2 is common everywhere, LB plus BH plus LH square units. This is the formula to find the TSA of a cuboid. Then the length of the diagonal. You can see there again by using Pythagoras theorem. Netra, tell me which triangle? In this figure, in which triangle do we apply Pythagoras theorem?
ABS.
AB? Yes, Netra?
ABS.
No, ABH. Okay, ABH. But according to the marking here, anybody else? Srijana, you did not attend the last physical class, right? Why? Srijana, no response. Raja, you're back in Trichy, is it? From Hyderabad?
Yes, ma'am. Just yesterday.
Okay, okay. So how did your competition go on?
Competition was well, but I did not get in. I did not win it.
No, no, that is okay. But you had a good experience.
Yes, ma'am.
You made new friends. You were
Yes.
exposed to something new and you learned something, right, from the competition?
Yes, ma'am.
Yeah, that is important. It's not about winning. All of us cannot always win, no? It's not about winning. It's about the new experience. It's about the joy you have, had with the new experience. So that is what is very important.
Yes, ma'am.
Yeah, yeah. We are always winners. We are never losers. We are all winners only. Okay, so yeah. Okay. So what is that new thing you learned from the competition?
Ma'am, just an exposure about the competition rules and
Oh,
regulations.
from your fellow competitors, you must have learned something, no? Even they would have learned something from you by just observing them. What have you learned, or is there anything that you got as a message from the competition?
While the competition was going, I was completely in the, how to say, in a stressful manner or something. Because it's my first time in under 17 category. Till date, I was playing in under 14 category.
Okay.
So the distance is varying for me.
Correct, correct.
First,
Okay. Now yesterday you were into which category?
not yesterday, ma'am, on Saturday, I was in
Saturday.
60 meters
Okay,
under
okay.
17 category.
Oh, so there are many children elder to you in this category.
Yes, ma'am. Even
Yeah.
11th standard brothers are playing with me. So
Correct, correct. Yeah, 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 yeah. So that was kind of frightening, right?
I was one of the youngest.
Youngest, right, right. Yeah, yeah, yeah. Uh-huh. My brother's son, he's a skater,
Oh,
roller skater. My God. I'll share his Instagram
sure, ma'am.
handle link. Okay, you can just have a look.
Yes, ma'am. Sure.
Yeah, yeah, yeah. Nice. Even I was very enthusiastic about sports when I was in school. I didn't take it keenly, but I don't know if I was a good athlete, but I was always there in the competitions and, running race and throw ball and all that, shot put. The school sports day, I'm saying, like, I was one of the members in the team. So always have a great passion for sports, though I could not chase my passion. I like sports and I like to watch. When I go to my children's school on sports day, I really enjoy the events. Maybe my children don't participate in them, but watching the other students, participate, that enthusiasm, I go back to my school days and I start living with them. So
Even
sports is very.
sports day events, but not as much as my archery.
Okay. Yeah, sports is very close to my heart. I love it. Nice.
Yes, ma'am.
Okay, good. If you can, you can just share some videos of your event where you have performed with me, if possible. Meaning, if you want, if you can,
Yeah,
like to see.
we did not take any pictures. Even my father was with me, but he was also just watching my match. He did not
Okay,
take any pictures or something.
okay,
Yes.
fine. All right, yeah. All right, children. Coming back to this. Yeah, I was asking which triangle I think. Okay, let me answer that question. So, by the marking here, see here. So, if you take this triangle BFH. If you take up this triangle BFH, in this triangle, when you apply the Pythagoras theorem, what is this one? This is the diagonal of the rectangle. What you see below, this line segment HF. HF is the diagonal of the rectangle. The base is the rectangle. See here, this base is the rectangle. This base is the rectangle. The whole thing is a cuboid, but this face is a rectangle. This face is a rectangle, this bottom face, and this is the diagonal of the rectangle, which is given by the formula root of L square plus B square. Root of L square plus B square is a formula to find the length of the diagonal of a rectangle. Rectangle is a plane figure. This is the formula. All right. And this is the height of the cuboid. Now, this is the length of the diagonal of the cuboid. This is the length of the diagonal of the cuboid, which can be found using Pythagoras theorem. So see here, this is the length of the diagonal of the cuboid. This one is root of L square plus B square. And this one is H. So how do we apply Pythagoras theorem? This diagonal square. Okay, diagonal square is equal to this one, the whole square. Root of Pythagoras theorem, children, square this one and square this one. The square on the hypotenuse is equal to the sum of the squares of the other two sides. So d square is equal to the square root and square. They are eliminated. So L square plus B square plus H square. So d is equal to square root of L square plus B square plus H square. So the length of the diagonal of the cuboid, the length of the diagonal of the rectangle is root of L square plus B square. The length of the diagonal of the cuboid is root of L square plus B square plus H square units. And like a cuboid also has 12 edges. Like a cuboid also has 12 edges. See here, 1, 2, 3, 4. 4 edges on the top, and in the bottom, 5, 6, 7, 8. So 4 on the top, 4 edges at the bottom, and you can see these edges, vertical edges, 9, 10, 11, 12. So like this, a cuboid also has 12 edges, but the edges are all not of the same length. All the edges do not have the same length like a cube. The length of this edge and this edge and this edge and this edge, the lengths of these edges are L. The length of these edges, 1, 2, 3, 4 are B, because of the breadth of the cuboid. And the length of these edges, 1, 2, 3, 4 are H. So in a cuboid, which has 12 edges, 4 edges are along the length, 4 edges are along the breadth, and 4 edges are along the height. You can see that I've marked. There are 4 edges along the length, 2 on the top and 2 below. 4 edges along the length, and there are 4 edges along the breadth. You can see there. On the side face, we have 2 edges. On the other side face, we have two edges of B units. So a cuboid has four edges along the length, four edges along the breadth, and four edges along the height. You can see the standing edges. They are the edges along the height. So the length of all these edges will be 4L plus 4B plus 4H. Why? Because L plus L plus L plus L, 4L. B plus B plus B plus B, 4B. H plus H plus H plus H, 4H. So it's not 12 here, 12 edges, but the length of all these edges is 4L plus 4B plus 4H units. Is it fine so far, children? Yes or no?
Yes, ma'am.
Yes, ma'am.
Now the next is a cylinder. The cross section of a cylinder is a circle. That is, again, you have many identical circles. You have many identical circles, meaning circles of the same radius. So say you have many circles of radius 5 centimeters. Okay, and you stack them. You stack these identical circles to a height, to some height. You place the circles one over the other, one over the other, one over the other, one over the other like this to a certain height, to a certain height. The solid obtained is a cylinder. The solid obtained is a cylinder. Circle. On top of that, you place another circle. On top of that, another circle. On top of that, you keep going like that. You keep going like that. So the solid obtained is a cylinder. The solid obtained is a cylinder. When you place identical circles or when you stack identical circles to any height, the solid obtained is a cylinder. And the cylinder is called a right circular cylinder. It's called a right circular cylinder. The cylinder is called a right meaning right angle to triangle. So that right cylinder, because the radius and height are perpendicular to each other. It's called a right is for the right angle. Okay, right angle, because the radius and height, they are perpendicular to each other. See, from this to this is the height of the cylinder. And this is the radius of the circle. Radius of the circle. The radius and height are perpendicular to each other. That's why right. Circular because the cross section is a circle. Right circular cylinder. Right because the radius and height of the cylinder are perpendicular to each other. Right circular because the cross section of the cylinder is a circle. Okay, so the cross section of the cylinder is a circle. So how do we express volume? It is the area of the cross section into height. Volume is area of the cross section into height, and the cross section is a circle. So what's the area of a circle? Pi r squared. Pi r squared. What is the area of a circle? Pi r squared. Height is h. So pi r square h cubic units, because volume is expressed in cubic units. Volume is expressed in cubic units. So pi r square h cubic units is the formula to find the volume of a cylinder. Curved surface area. The curves, now the cylinder, the entire cylinder is made up of three parts. One is the curved surface area, then the area of the top, the circle on the top, and the area of the circle at the bottom. Okay, so you can look at the cylinder in three different parts. One is the curved surface area, the curved surface area of the cylinder, which is the curved surface area, this portion, this one. That is the portion not including the circle on the top and the circle at the bottom. The rest of it is the curved surface area. In a cylinder, leave the circle on the top and leave the circle at the bottom. The body of the cylinder, the curved body of the cylinder is the curved surface area. This curved body of the cylinder, the curved body of the cylinder is the curved surface area. The curved surface area does not include the area of the circle on the top and the area of the circle at the bottom. It does not include that. So not this, not this. The rest of it is CSA. Don't take the circle on the top. Don't take the circle at the bottom. The rest of the figure is curved surface area. All this is the curved surface area. So curved surface area is perimeter of the cross section into height. That's what we have been writing everywhere. Everywhere. CSA is perimeter of the cross section into height. And what is a cross section? The cross section is a circle. And what is the perimeter of the circle? The circumference, 2 pi r. Perimeter of a circle is 2 pi r. Into h. So 2 pi r h square units. Area is expressed in square units. Volume is expressed in cubic units. Next is the total surface area. So total surface area is the curved surface area plus the area of the base or the bottom plus the area of the top. What's the CSA? What is the curved surface area? 2 pi r h. We found here 2 pi r h. What is the area of the base? The base is a circle. The base is a circle. What's the area of the circle? Pi r square. Area of the top. What is the top? It's a circle. What's the area? Pi r square. So 2 pi r h plus 2 pi r square, because pi r square plus pi r square is 2 pi r square. 2 pi r h plus 2 pi r square. 2 pi r common. 2 pi r common. See, 2 pi r is common. So in the bracket h plus r or r plus h, because see here 2 pi r h plus 2 pi r square. So you're taking out 2 pi r common, 2 pi r common. So if 2 pi r is common, you should write h. Then 2 pi r is common plus r or r plus h. 2 pi r into r plus h. Is this okay, children?
Yes, ma'am.
All right. Now, a cone does not have a uniform cross section because you cannot arrange identical, things and get a cone. You cannot know a plane figure, no identical plane figure you can arrange to get a cone. Because it does not have a uniform cross section. Because it does not have a uniform cross section. So a cone does not have a uniform cross section. Volume of a cone, 1 by 3 pi r square h. Now the volume of a cylinder is pi r square h. The volume of a cone is 1 by 3 pi r square h. Because if you have a cylinder, of radius r and height h, and supposing you have a cone of radius r and height h. Now supposing these are two containers, you have a cylindrical container like this, you have a cylindrical container like this and a conical container like this. Using this conical container, you should fill water into the cylinder 3 times. You fill this cone with water fully, pour it into the cylinder. Then again fill water completely in the cone, pour it into the cylinder. Then again completely fill water in the cone and pour it into the cylinder. You will see that after pouring pouring water from the cone 3 times, the cylinder is full. Both the solids have the same radius and same height. Both the cylinder and the cone have the same radius and height. So if you have a cylindrical vessel and a conical vessel, you must fill the cylindrical vessel 3 times using the conical vessel. That means what? The area of the cylinder is 3 times the area of a cone. That is why the area of a cone, the volume of a cone is 1/3 the volume of a cylinder. 1/3 the volume of a cylinder. The volume of a cone is 1/3 the volume of a cylinder. Then the curved surface area. These you just have to remember, children. Curved surface area is given by pi r L square units, where L is equal to root of h square plus r square. H is the height of the cone and r is the radius of the cone. Radius will be given, height will be given. Substitute and find L, and then you can use the formula pi r L. And finally, the total surface area. Now the cone is made up of two, surfaces. One is the curved surface area, and the other is the circle at the bottom. The cone has only two parts. One is the curved surface area, and the other is the area of the base or the area of the bottom. So the total surface area of a cone is equal to the curved surface area plus the area of the base. Curved surface area is pi r L. Area of the base is pi r squared. Take out pi r common and you get L plus R. So pi r into L plus R or R plus L. However, pi r into R plus L is the formula to find the TSA of a cone. What did I tell you? If you have a cylinder of radius R, okay, let's take a example like this. Supposing you have a cylinder of radius 7 and height 10 units, and you have a cone of radius 7 and height 10, same thing, 10 units. Cylinder radius 7, height 10, cone also radius 7, height 10. So now using this cone, you must fill liquid into this 3 times. 1, pour it inside. 2, pour it inside. 3, when you pour it inside, it will come to the brim. That's why we say volume of a cone is 1/3 the volume of a cylinder, pi r square h. 1/3 into pi r square h. That's about the cone. And you can see here, this is called the vertical height of the cone, h. This is a vertical height of the cone. This is the radius of the base, and this is called the slant height of the cone. This is called the slant height of the cone. L, which is represented by L. The slant height of the cone is represented by the letter L. Now again here Pythagoras theorem. Everywhere we have been using Pythagoras theorem. So here also by Pythagoras theorem, L is equal to root of h square plus r square. Any questions, children, here?
Clear, ma'am. No, ma'am.
Next is a sphere. Next is a sphere. So while again, a sphere does not have a uniform cross section. A sphere does not have a uniform cross section because a solid like a sphere you cannot get by arranging identical, things. You can arrange, you can stack to form a sphere, but you cannot stack identical plane figures to get a sphere. The cross section of a sphere or a sphere does not have a uniform cross section like a cube, which is a square, or a cuboid, which is a rectangle, a cylinder whose cross section is a circle. So like that, for a sphere, you do not have a uniform cross section. Volume of the sphere is equal to 4/3 pi r cubed. What you can see here is h is not there. Everywhere there was h, no? Because when it comes to area, we do not have h. So when this one does not have a uniform cross section, just remember the formula. Volume is equal to 4/3 pi r cubed cubic units. Sphere. Volume of a sphere is equal to 4/3 pi r cubed cubic units. Total surface area. Now here you cannot differentiate. In a sphere, you cannot differentiate between the curved surface area and the total surface area. You cannot say that from here to here is curved surface area and the rest and all this put together is a total surface area. No, you cannot differentiate between the total surface area and the curved surface area. So it's the same here. In a sphere, it's the same. The curved surface area, total, the full thing, the exterior is the total surface area, which is given by the formula 4 pi r squared. 4 pi r squared. Now here h is not there. You can see it's only 4 pi r cubed. Sorry, 4 by 3 pi r cubed. Everywhere we had h, no? Everywhere we had r and h, r and h. In the cylinder also we had r and h. The cylinder also we had r and h. But here, see, there's only r. That is because this is the height of the sphere. This is the height of the sphere. This is the radius. This is the radius. So the height of the sphere is nothing but twice the radius, 2r. If the radius is r, or if the radius is 6 centimeters, the height of the sphere is 12 centimeters. So there is nothing. So h is also written in r only here. There is nothing like h here because h also is expressed in r. H is equal to 2r. Height of the sphere is twice the radius. See here, this is the radius. This is the radius, r. The height of the sphere is from here to here. From here to here, this one is the height of the sphere. This one is the height of the sphere. Okay, this one is the height of the sphere. From here to here, it is radius. From here to here, it is radius. So r plus r, 2r is the height of the sphere. H is equal to twice the radius. So since h is equal to 2r, that's why we have r cubed here. All the while we were having only r squared. So since the height is also in r, the height is also in r, the volume of a sphere is 4 by 3 pi r cubed cubic units. And the TSA is 4 pi r square units. Now in a hemisphere, which is a half of a sphere, hemisphere is half of a sphere. Here you can differentiate between total surface area and curved surface area. Okay, because now the top portion, see this portion, this top portion, it's a circle. And apart from that, this entire thing is a hemisphere. The entire thing is a hemisphere. This full thing is a hemisphere. The top is a circle. The top is a circle. Now leave the circle. The rest of it is the curved surface area. The rest of it is the curved surface area. The flat circle on the top. On the top, there is a flat portion, which is circle. Leave that. The rest of the body of the hemisphere is the curved surface area. Now you imagine you have a hemisphere in your hand. You have a hemisphere in your hand. That is hemisphere is, if you take a cork ball, if you cut it into 2 equal halves, each half is a hemisphere. A cork ball is a solid sphere. A cork ball is an example of a solid sphere. Football and other things, there's only air in it. It's not a solid sphere. It's not, see, like a football or, any other ball which, you used to play is filled with air inside. So that's not a solid sphere. It's a hollow sphere. Hollow because it's empty inside. The balls in which you fill air inside is a hollow sphere. Cork ball is an example of a solid sphere. Cork ball, solid sphere, because it's completely made of material. The others are hollow spheres because there's only air inside. Now, when you take a cork ball and you cut it into 2 equal halves, each half is called a hemisphere, a solid hemisphere. When you take a cork ball and cut it into 2 equal halves, each half is called a hemisphere. It's a solid hemisphere because the cork ball is a solid sphere. So when you cut it into two equal halves, each half is a hemisphere, a solid hemisphere. Now you can touch the circle on the top. You can touch the circle on the top. Leave that circle. The rest of the body is called the curved surface area. The curved surface area. Now the curved surface area plus the area of the top is a total surface area. The curved surface area plus the area of the top together is the total surface area. So here a hemisphere has only two parts. One is the area of the circle on the top. And leave that circle on the top, the rest of the body, that curved thing is the curved surface area. The top is a circle, pi r square. Apart from the circle, the body of the hemisphere is called its curved surface area. It's given by the formula 2 pi r square. The total surface area will be 2 pi r square plus pi r square. This is 2 pi r square. And this one area is pi r square because it's a circle. So 3 pi r square is the total surface area. Volume is 2 by 3 pi r cubed. And here the height of the hemisphere is equal to its radius. Radius, which is the height of the hemisphere. You can see it in the figure. See the depth of the hemisphere, which is the height. It's equal to the radius. In a sphere, the height is equal to twice the radius. In a sphere, the height is equal to twice the radius. In a hemisphere, the height of the hemisphere is equal to the radius of the hemisphere. The height of the hemisphere is equal to the radius of the hemisphere. So volume. So again, a hemisphere does not have a uniform cross section. Half of a cork ball is a hemisphere. It's a good example for a hemisphere. It's a solid hemisphere. There is a circle on the top and then the curved portion of the ball. The curved portion alone is the curved surface area, including the circle on the top is the total surface area. Now the next thing is a cylindrical shell or a hollow cylinder. Now you might have all seen this sellotape bundle, no? It looks something like this. The sellotape roll. Can you all imagine that one? Or if you have one in your house, you can go and get it.
Yes, ma'am.
Okay. Now, this sellotape roll is a very good example for a hollow cylinder. It's hollow because you can see from one end, you can see the through the other end. So it's hollow. It's a hollow cylinder because it's cylindrical. The sellotape is cylindrical, so it's a cylinder. It's hollow because you can look through the cylinder. From one end, you can look through the other end. Now you observe that the wall of the sellotape bundle will be thick. The wall will be thick. The wall of the sellotape bundle, it will be thick. So so you imagine, or you when you look at this, you think of the sellotape roll. When you look at this, think of the sellotape roll. It looks something like this. So there is one circle here with radius small r. There is another circle here with radius capital R. The radius of the inner circle is small r, outer circle capital R. And the thickness of the wall will be given by the letter W. W is the thickness of the wall. Then, of course, you have the height of the tape. This is the height of the tape or the sellotape bundle, this one. That will be given to you. Okay, so what is a hollow cylinder? Hollow means you can look through the cylinder. That is, the circular ends are open. Hollow meaning the circular ends, they're open. From one end, you can look through the other end. So hollow, it's a cylinder. It's also called a cylindrical shell. Now, what are the different parts of this hollow cylinder? So the circle on the top has a radius of r units. The circle on the top on the outside has a radius called capital R units. So on the top, you can see a ring. You can see a ring on the top. You can see a ring on the top. See between these two circles, between this circle and this circle, between this inner circle and outer circle, you can see some area here. This area is called the area of a ring. That's called the area of a ring. What is the area of the ring, children? What is that ring? The ring is the area between two concentric circles. See, there is one circle here. There's another circle. There's another circle going around it. This one is the area of the ring. So you can see here, there is one inner circle here on the top. There is one outer circle here on the top. Now this one is called the ring, area of a ring. And this one is the height of the cylinder. This is the height of the cylinder. So hollow cylinder will have two R's, one small r and one capital R and H. Now, what is the volume of the material in the cylindrical shell? What is the volume of the material in the cylindrical shell? So the volume of the material will be the external volume minus the internal volume. What is the external volume? Externally it is a cylinder, internally it is a cylinder. So external volume will be pi. It's a cylinder, right? So pi r square h, but capital R. H is the same. Internal volume is pi r square h because again it's a cylinder, but smaller, pi r square h. External volume minus the internal volume will be the volume of the material. The volume of that material, that is that sellotape. The volume of this material, this thick material, is pi r square h minus pi r square h, which wherein pi h is common, r square minus r square cubic units. Or you can interpret the volume of the material as also area of the uniform cross section into height. Because this one has a uniform cross section. I'll just come back, children. Just a minute. Thank you, children. Yeah, so what was I telling you that, yeah, so in we call it a hollow cylinder because you can look through from one end, you can see through the other end. And in this hollow cylinder, you can see there's an inner circle here, there's an outer circle here, and there is some area between the two circles. There is some area between the two circles, which is called the area of a ring. Area of a ring. And we also say that the uniform cross section of a hollow cylinder is a ring. So imagine you have many rings like this, many rings. You you could have, I think you should have noticed the washer between a nut and a bolt. Between a nut and a bolt, there's something called a washer. It's a metal plate. This is how it will be like, it'll be hollow here. It'll be hollow here. There's a plate. Here there'll be the metal. There'll be metal here, but this is hollow. If you have many pieces like this and you stack them one over the other, you will get a hollow cylinder. Okay, imagine this one. This is a plate. Okay, this is a plate. See this one. This is a metal plate like this. This is a metal plate. Like this, you have many pieces. Like this one, you have many identical pieces. So if you keep this one over the other, if you stack this, you will get a hollow cylinder like this. We'll say that this is the metal plate or a metal ring. You have many pieces like this. You place them one over the other, you'll get a solid, you'll get a hollow cylinder like this. It's hollow because you can see through. So again, you have the height of the cylinder. Here you have two radius, one inner radius and one outer radius. That is the radius of the inner circle, which is the inner radius, the radius of the outer circle, which is the outer radius. And of course, the height of the cylinder, h. The volume of the material is extra. We can interpret the volume in two ways. Here we can interpret volume in two ways. One is volume is external volume minus internal volume. See how I can relate this for you. Supposing you have a rectangle. Inside a rectangle like this. Don't you remember? Now supposing the area of this the length of this rectangle is 10 by 7 and this one is something like 12 by 10. Okay. So what will be the area of this region? What will be the area of this region? Tell me. What will be the area of this region, children? You don't know? Okay. The area of the shaded region will be the area of the outer rectangle, 12 into 10, minus the area of the inner rectangle, 10 into 7. Now you understand?
Yes, ma'am.
Yes, ma'am.
Yeah. So the area of the shaded region is equal to the area of the outer rectangle, 12 into 10, minus the area of the inner rectangle, 10 into 7. The area of the shaded region. Similarly, like how you say area of the outer rectangle minus area of the inner rectangle is the area of the shaded region. In the same way here, volume is the external volume minus the internal volume. The volume of this material will be the external volume minus internal volume. So since it's cylindrical, the external volume is pi capital R square h and the internal volume is pi small r square h. See, how will you now, supposing, you have a manufacturing unit, how will you make a hollow, cylinder like this? You have a manufacturing unit and you manufacture, hollow cylinders like this of metal. How will you do this? It's like as if with a solid, as if, you make a solid cylinder first. It's like as if you make a solid cylinder first, and from the solid cylinder, it's like you're removing another cylinder from the middle. From a solid cylinder, if you remove another cylinder from the middle, that's why this is empty. That's why this portion is empty. It's like as if this were completely solid earlier. And from that one, you've drilled out a cylinder from the middle. From that, you've drilled out, you've taken away a cylinder from the middle. That's how you can understand this solid, this hollow cylinder. This hollow cylinder is like as if it was first solid, like this, whose volume is pi r square h. And from that, you're taking away something. What are you taking away? From this, you're taking away a cylinder from the middle. You're removing a cylinder from the middle. What's the volume of that cylinder which you're removing? Pi r square h. The radius will be different, that's all. The height will be the same. The radius will be different. Volume of cylinder is pi r square h. So from a big cylinder of volume pi r square h, you're removing a small cylinder of volume pi r square h. So the volume of the material is the external volume minus the internal volume. When you take pi h common, capital R square minus small r square cubic units. Or you can even say the volume of the material is, because volume is always area of the uniform cross section into height. Volume is always area of the uniform cross section into height. And what is the uniform cross section? It's a ring. We understood that many rings, if you place like this, you will get a hollow cylinder. It's a ring. And how do you find the area of a ring? It's the area of the outer circle minus the area of the inner circle. So which is pi r square minus r square. Area of this portion is area of the outer circle, pi capital R square, minus the area of the inner circle, pi small r square. So when you take pi common, r square minus r square. So the area of the cross section, which is a ring, is pi r square minus r square into height h. So pi h into capital R square minus small r square cubic units. You can understand it anyways, this way or this way. That's about a hollow cylinder. Example I told you is a sellotape roll. It's continuing here. Hollow cylinder continues here. Now area of one ring, I told you, pi capital R square, area of one ring, this ring on the top, is outer circle, area of the outer circle minus area of the inner circle. When you take pi common, r square minus r square square units. This is the area of this flat ring on the top, or this ring, the area of this portion. So the area of two rings will be 2 into that. The area of two rings will be 2 into this one. 2 into pi r square minus r square, which is 2 pi r square minus r square square units. Now talking about the curved surface area. Now this hollow cylinder, it will have two curved surface areas. One is on the outer, see here on the outside. On the outside it has a curved surface area. Then in the inside, this is also the curved surface area. Inside cylinder, the outer cylinder has a curved surface area on the outside. The inside there's a cylinder, no, that also has a curved surface area in the inside. You can touch it and feel it. You should imagine a sellotape bundle for that, a sellotape roll for that. On the outside, you can touch the curved surface area. Then in the inside also there's a cylinder. That also has a curved surface area. So the curved surface area is the external CSA plus the internal CSA. See, if it is a solid cylinder, you cannot touch the inside. Curved surface area will be only on the outside if it's a solid cylinder. So in this figure, which you see here, 1 minute. Yeah, in this figure you see here, you can see a cylinder inside and its curved surface area here. And then on the outside, you have a cylinder with a curved surface area here. So the curved surface area is the external CSA plus the internal CSA. External CSA is 2 pi capital R square h. Because what is CSA formula? Cylinder CSA, what's the formula? 2 pi RH. Cylinder CSA is 2 pi RH. Okay, so when it is the outside CSA, it is with outside radius. Inside CSA with the inside radius. Only the radius will change. The height will be the same. So the external CSA plus the internal CSA. 2 pi smaller h, 2 pi capital H. You can take out 2 pi h common and have this. This is the curved surface area. Remember, curved surface area is the area of the two portions. One curved surface area inside and one outside. Then the total surface area. Now imagine you have to paint this hollow cylinder. Where all will you paint? If you have to paint this hollow cylinder, where all will you paint? Inside, the inner CSA you will paint. Then on the outside, the outer CSA. Then there's one ring on the top and there's one ring at the bottom. Only when you paint all this, you have painted the total surface area of the hollow cylinder. So again, you'll have to imagine well. Imagine a hollow cylinder like this. You can see the figure. You want to paint it all over. So that will be the total surface area. You want to paint it all over. That will be the total surface area. So you started painting. So you paint the inner curved surface area. Correct. You paint the outer curved surface area. Correct. Is that over? No. There is one circle on the top and there's one circle at the bottom. I'm sorry, a ring. When I say the circle, it's a ring. There is a ring on the top and there's a ring at the bottom. So we say that the total surface area is the curved surface area. That is the inner CSA plus the outer CSA plus the area of two rings. The inner CSA plus the outer CSA plus the area of two rings. CSA meaning inner CSA plus outer CSA plus the area of two rings. Yes or no, children? The four parts in a hollow cylinder. Do you get that?
Yes, ma'am.
So if you look carefully at the sellotape, inside there is one curved surface area. Outside there's one curved surface area. So inner CSA plus outer CSA plus the area of one ring on the top and another ring at the bottom. So maybe you can write this one like this. Inner CSA, you can split it like this. Inner CSA plus outer CSA plus area of two rings. Plus area of two rings. You don't have to actually see, children, this formula you really don't have to memorize. Now today I'll not tell you this because maybe it's too much for today. So I'll not tell you. You can find it separately. How separately? If you have to find the total surface area, find the inner CSA. Find the inner CSA 2 pi RH. Then find the outer CSA, which is 2 pi capital RH. Then find the area of one ring. You've done the inner CSA and outer CSA. Now the area of one ring on the top, pi r square minus r square into 2 will be the area of two rings. So the total surface area is the inner CSA plus the outer CSA plus the area of the ring on the top plus the area of the ring below. So two rings basically. Inner CSA, outer CSA, and area of two rings, one on the top and one at the bottom. So you don't remember this now, children. You can just work it separately. Find the inner CSA 2 pi RH. Then find the outer CSA 2 pi RH. Then the area of two rings. One ring is pi r square minus r square. So two rings will be 2 into pi r square minus r square. Find all these answers and add. That's all. That's the total surface area. So if you have a hollow hemisphere like the figure you see, if you have a hollow hemisphere, so whenever it is hollow, the volume is external volume minus internal volume. For a hemisphere, we just saw the formula. See it? Hemisphere 2 by 3 pi r cubed. Okay. All right. So the volume of the material in a hollow hemisphere will be external volume minus internal volume. External volume minus the internal volume. External volume is volume formula is 2 by 3 pi r cubed. Volume, the formula is 2 by 3 pi r cubed. So 2 by 3 pi capital R cubed minus 2 by 3 pi small r cubed. When you take out 2 by 3 pi common, you get r square minus r square. Sorry, r cubed minus r cubed cubic units. When you take out 2 by 3 pi common, r cubed minus r cubed cubic units. External volume is 2 by 3 pi r cubed because that's the volume of a hemisphere. That's the formula to find the volume of a hemisphere. 2 by 3 pi r cubed. So just change the radius, capital R, small r. You will get the volume. Subtract, you will get the volume of the material. 2 by 3 pi common, r cubed minus r cubed cubic units. Now what's the curved surface area? Again, if you observe carefully, there will be one inner CSA and one outer CSA. On the outside, there will be a curved surface area, and on the inside, because it's hollow, no? Half of a coconut is an example of a hollow hemisphere. When you buy a full coconut and you break it into 2 equal pieces, each piece is a hollow hemisphere. Assuming that a coconut is perfectly spherical, when you cut that or you break it into 2 parts, 2 equal parts, each part is a hollow hemisphere. Each part is a hollow hemisphere. So the volume of the material is external volume minus internal volume. For hemisphere, it is 2 by 3 pi r cube. So just take the different radius, capital R and small r. 2 by 3 pi common, r cube minus r cube cubic units. CSA is internal CSA plus external CSA. CSA formula is 2 pi r square. So with small r and capital R. So 2 pi common and you have r square plus r square square units. Total surface area will be the CSA, that is the inner CSA plus the outer CSA plus the area of one ring on the top. There is a ring on the top. You can see that ring here. This is the ring which is on the top. This is the ring on the top. So the total surface area will be the curved surface area and the ring together. Because the ring is on the top, that will not come in CSA. In CSA, the ring will not be included. In CSA, only the inner CSA and outer CSA will be included. Plus the ring on the top will make the total surface area. Don't worry about this formula again, children. We can work it separately. You can find the inner CSA, 2 pi r square. Then find the outer CSA, 2 pi capital R square. Then find the area of one ring, pi r square minus r square. Add all this to get the total surface area of a hollow hemisphere. Now this one is a spherical shell or a hollow sphere. You can see this figure. This one is a hollow sphere. They have cut it into 2 parts and giving you the inner view. That's a hollow sphere. Hollow because it's empty inside. They have cut it into 2 parts and they're giving you the inner view. That yellow portion is the inner view. There's a sphere inside, but it's empty. There's a sphere inside, but it's empty. There's a spherical shape inside, but it's empty. That's why we call it hollow sphere. So again, whenever it is hollow, the volume is external volume minus internal volume. Whenever it is hollow, the volume is always external minus internal. And for a sphere, the formula we saw earlier, 4 by 3 pi r cube. All right. So 4 by 3 pi r cubed. Oh. Yeah. So whenever it is hollow, it is external volume minus internal volume. It's a sphere, no? So 4 by 3 pi r cube minus 4 by 3 pi r cube. 4 by 3 common. 4 by 3 pi common. R cube minus R cube cubic units. And the volume of the space inside the shell will be the volume of the smaller, the innermost sphere. The volume of the space inside the shell. Inside the shell, the volume of the space inside the shell will be 4 by 3 pi r cube, small r cube units. Because inside the shell, there's a sphere. There's a spherical cavity. And the volume of that space will be the volume of the spherical cavity, 4 by 3 pi r cubed, cubic units. All right, children, I want you to write down all this now quickly. Take a screenshot. All of you complete this in your classwork and share the pictures. You should not leave the meeting before you complete. Take a picture, children. Or we'll do one thing, 1 minute. Take a picture. Take a screenshot.
Okay, ma'am.
All right. Let me clear it. Or let this be that. Yeah, take a picture.
Okay, ma'am.
I'll just clear the slide. Yeah, take a picture.
Okay, ma'am.
Yeah, picture.
Okay, ma'am.
Yeah. Yeah, 1 second. Take a picture, children. Done this one. Done, children.
Yes, ma'am.
Yes, ma'am.
What's the next one? Okay, that's all. Yeah, all this, all of you have to complete it today and share the pictures with me. Or I'll give you time till tomorrow. By tomorrow evening, all of you should complete the notes and the pictures you have taken and share it on WhatsApp with me. Is that fine?
Yes, ma'am.
Yes,
All
ma'am.
right. Now try to just go through the screenshots and I'll ask you questions from here. Just quickly have a look at the formulae from the screenshots. Just one glance, Just take a interesting test. I'll give you 5 minutes for that. I'll put myself on mute. I'll give you 5 minutes for that. Simply go through all the formulae, the final thing.
Completed, ma'am.
That is the main character. Wow.
All right, children. Tell me, what is this? 6a square units. Don't look into the book. 6a square units. What is that?
Total surface area of cube, ma'am.
Total surface area of a cube. The area of all the six. The total surface area of a cube. The total surface area of all the six faces of a cube. Very good. What is the root of L square plus B square plus H square?
Length of cuboid.
Length of the?
Cuboid.
The length of the diagonal of a cuboid. Very good. What is 1 by 3 pi r square h?
Volume of the cone.
Volume of a cone. Very good. Volume of cone. What is 12a? What is 12a?
Edge of a cube, ma'am.
The length of all the 12 edges of a cube. What is root 3a?
Length of a diagonal of a cube, ma'am.
Length of the diagonal of a cube. Very good. And what is this one? What is 2 pi RH plus 2 pi RH? When it is somebody's mic is enabled, please disable your mic. Yeah, what is 2 pi RH plus 2 pi RH, children?
TSA of hollow cylinder, ma'am.
TSA, huh?
CSA, ma'am.
CSA, correct?
Yes, ma'am.
Yeah. The inner CSA plus the outer CSA. 2 pi capital R H is the outer CSA plus 2 pi small r H is the inner CSA. What is 4 pi r square?
Total surface area of a hollow sphere, ma'am.
TSA, total surface area of a sphere. Good. All right, children. So please memorize the formula by the next class. So next class we'll start, solving questions based on these solids: cube, cuboid, cylinder, cone, sphere, hemisphere, and the hollow hemisphere, hollow sphere, hollow cylinder, and all that. Okay, so memorize all the formulae, children, by the next class. So that's it for today's session, children. Thank you so much. Good night.
Thank you.
Thank you, children. Good night. Thank you. Good night.